Welcome back to NET Physics series. And today we'll continue with the chapter number 8, which is of waves. So this would be the part 2, the final part of the theory of waves. So let's continue by listing some of the factors on which the speed of sound depends on. So at first we have that the speed of sound, let's denote it by V, it depends inversely to the square root of the density of the material, right? And then we have that the speed of sound depends directly proportional to the square root of the temperature of the medium. And so from which we can write down the speed of sound ratio for one medium to another medium as square root of T1 by square root of T2. So if I look at this expression, the first one, this really implies that, for example, you have a hydrogen atom, which if I draw would look something like there is a proton in the nucleus, and then there is just one electron in the orbit of that nucleus. And so this is my hydrogen atom. And if I compare this with the oxygen atom, which is in the Bohr's picture, it looks like you have protons, you have 8 protons, and you have 8 neutrons. And so let's draw the electrons as well. You have 2 electrons in this shell, and so I'll just use these dots to represent these electrons, so I'll not write electrons every time. Then you have 6 more in the outermost orbit, so 1 2 3 4 5 and 6. So if you compare these two atoms now, if I compare these two atoms, clearly oxygen atom is more dense compared to the hydrogen atom, which means that the speed of sound is really approximately 4 times more than the speed of sound in the oxygen atom. So the speed of sound in a hydrogen atom is approximately, you can say, 4 times more than the speed of sound in the oxygen atom. And that is simply because the hydrogen atom is much less dense compared to the oxygen atom, where it has 8 protons, 8 neutrons in the nucleus itself, while hydrogen atom just have a single proton in its nucleus and just 1 electron. You can think of this second expression, which is velocity of sound is proportional to the square root of the temperature, right? Think in terms of what is happening when the temperature increases. We know that for molecules, if I write their kinetic energy, it is something like 3 by 2 kT, where T is the temperature, K is really, this is the Boltzmann constant. And so the speed of the molecules, atoms, it depends on the temperature directly. So if I increase temperature, the way that the atoms really are moving, they'll start moving very rapidly. So they would start jiggling around much faster. And so if they're jiggling much faster rather than being compactly packed in a space, this thing is more dense, right? So when they're compact in a space, when the temperature is low, the atoms are almost at rest. In that case, the density is high, right? And in this case, when the temperature is high, atoms are jiggling around here and there, the density is also low. So the speed of sound in that case, where the temperature is high, would be more, right? So here speed of sound is high, while here the speed of sound is low. You can easily relate this back to the density of the molecules or atoms, or the system for that matter. Now let's move on to what is known as the principle of superposition. So the principle is something like this, that if I have a wave that maybe looks something like this, and then I have another wave which I can add to this wave, suppose that wave is also something like this. Now once I add these two waves, which really means that these two waves are simultaneously approaching each other, then the resultant of these two waves is just the sum of these individual waves, right? So this means really that the resultant of these two waves will give me a wave with a much higher amplitude, really, in this particular example, which really means that all I'm doing is adding the displacements. Let's suppose that we have displacements x, then the total displacement of this wave is really the sum of the displacements of these two separate waves. If this was x1 and this was x2, then this would be just simply x1 plus x2. Now this principle is valid for more than one waves. In fact, you can add up to n in number of waves, so any number of waves. So this could really go to x3 plus x4 and up to some random xn. So that's how you add your waves together. The displacements of the waves are really added together, and this principle is known as the principle of superposition. Now this principle of superposition has many applications as well. The first application is known as interference, and the name really says it all. It is really just when two waves, if we come back to this example, two waves are interfering with each other. So it is really, interference is produced when two waves are superimposed with each other, but the condition is that the two waves superimposing waves must have a same frequencies, right? Their frequencies should be equal, and the two waves which are moving, they should be moving in a same direction. And when this happens, it implies that the two waves are actually interfering with each other. So if you think about, read the statement is implying what you normally think of what interfering really means. So the two waves, they have same frequencies, they are moving in the same direction, which means that these two waves are really interfering with each other. Now, if everything is the same, however, we have different frequencies, slightly different frequencies, then we have a phenomena of beats. And beats are really produced when the same thing happens, but let's write it in this way. We have superimposing waves. They are traveling in same direction, but their frequencies are slightly different. When this happens, we call this thing that we are really producing what is known as beats. So if I draw those beats, really, it looks like, so for example, I have a wave which is something like this, right? And you can say that this wave, it might have some frequency, let's say it is 700 hertz, for example, and I add to this another frequency, which is slightly different frequency. You could say that this frequency is, let's say that this is 705 hertz. Then these two things would really produce something that looks like this. And this would be really a beat, right? Which is produced by the sum of these two slightly different frequencies. The next application is to the stationary waves. Now remember, these applications are for the principle of superpositions, and stationary waves are simply produced when you have two waves which are of the same frequencies. So you can say maybe this is a wave and then you have the similar wave. Let's just copy paste this thing. So we have these two waves, but the condition at this point is that these two waves must be of their frequencies omega 1 is equal to omega 2, and their amplitudes x naught 1 is equal to x naught 2 should also be same, and they are moving along the same line. So they should be moving along this same line. However, one is moving in this direction, then the other one should be moving in the opposite direction. So the directions should be opposite to each other. So you can say opposite directions. So whenever you see something that fulfills all of these three conditions together, then we say that the resultant wave would be a stationary wave. So coming back to the beats case, let me just quickly write down an expression on how can I relate the frequencies of these two waves to the frequency of the beat. So we can define something that is called as the beat frequency, and it is really just the number of beats produced per second. So you can then define or write an expression for frequency of beats in terms of the frequency of the two waves which produced a beat as the modulus of frequency of the first wave minus the frequency of the second wave. So the mod ensures that the beat frequency is always positive. Now we can also further talk about interference. So let's discuss interference in a bit more depth. Interference. Now remember, or just know that the interference can exist in two forms. So first we have constructive interference. Now constructive interference is when you have two waves which are, so for example, this is one wave, and then let's say that you have another wave which is in phase with this one. So you could just say that you have another wave which is in phase with this wave, which would really mean that the path difference between the two waves. So if I just let me just copy paste this wave. So here we have this wave. Now if the path difference between these two waves is of n lambda, so the difference between the path is equal to n lambda, where n is any integer, right? It belongs to the set of integers, and lambda is the wavelength of the wave. So if this wave, instead of being here, it could have been here, it would produce constructive interference. It could be just one lambda like this, which means that this difference is of 1 lambda, right? Because that's one wavelength. So that's the difference of 1 lambda. So these waves could be moving like this, and still the interference is constructive. So you can see that if you look at the diagram. This point is matching with this point, so they're both in the same direction really. So they would just add. So the displacement, so suppose this is 0.1, this is 0.2, x1 plus x2 will produce some other x which would be higher, greater than x1 plus it would be greater than x1, and it would be greater than x2, right? So it would be the sum of these two things. Then we have another thing which is known as destructive interference. Now in destructive interference, the path difference is of n plus 1 by 2 times lambda. Now remember, in this case, the value of n could be plus minus 1, plus minus 2, and so on, right? And it can also be 0 is also over here. Similarly, in this case, n can be 0, plus minus 1, plus minus 2, and so on. So the minus just makes this wave, the second wave, it would just make this wave move towards in the negative direction, right? So it would move, I cannot really draw it over here properly, but it would just move 1 lambda behind this thing, right? Okay, so that's what would happen if you have negative n. Now in destructive interference, we could have a wave that is like this, and the other wave, which would be, let's just move this a bit here and then have another wave. Now if this wave is something like this, so that's n plus half. This is the difference in these two is of n plus half lambda. So you can clearly see that this is a value in one direction, and these amplitudes, remember, the amplitudes have to be equal. So if I look at this one, I have this point, and if I look at this one, I have this point over here. And if I add these two, because this is in the up direction, so this would be some positive value, and this would be, because it's in the opposite direction, it's downwards, so this would be a negative value. And then when I would add this, it would be something like x2. If I call this 2, let's just call it 1, and let's just call this 2. So x1 is this one, it's positive, plus minus x2. And because the amplitudes are the same, then this would be really x1 minus x2 and 0. So hence the amplitude is being cancelled out, so the resultant would be something like this. So it's destructive. The wavy things have really cancelled out each other, and hence the interference is known as a destructive interference. It is also the silence region, right? Because there is no waves, so it's just something that where we have no signal at all. And for constructive interference, it's known as the echoing zone. Moving on, let's talk about standing waves. So these standing waves are also what we called stationary waves, and the superposition of two identical waves traveling in opposite directions to each other in the same medium will give rise to these standing waves. Now, both constructive and destructive interference takes place in the formation of these type of waves. If I look at this diagram, here we have one wave like this, and we have another wave like this, and there are these points where these waves are coinciding or intersecting with each other. These type of points are called nodes of the wave. And the points that lie like this in between these two nodes, these are called anti-nodes, and we can represent them with A. So really the points of where we have constructive interference, these points, right? So here we say that the points where we have constructive interference, these are called antinodes, and where we have destructive interference, where you can see the waves are joining each other at these points where it comes to 0 really on this axis. These points are called as nodes, and the nodes are where we have destructive interferences. So this distance from this node to this node is really lambda by 2, right? So it is this distance. So the distance between two nodes is always half of wavelength, while the distance between an antinode and a node is half of this half wavelength, which is just lambda by 4. Now, where we have antinodes, really, at that point, the energy stored in these antinodes is really at their extreme positions, right? So this is the amplitude or the extreme position we can talk about in terms of oscillations. It's known as the extreme position. And so the energy which is stored at these antinodes is entirely potential energy, while when these are constructing like this, or sorry, destructively interfering like this, where we have nodes, at this point the entire energy is the kinetic energy. You can think of this thing in terms of a pendulum and a bob, where this thing, if I have it like this, where it's at mean position, this is really what we are referring to as the node, while the extreme position of this pendulum or a bob is what is we are referring to as the antinode, where this distance is the amplitude of this oscillation. It is the same case over in this diagram. So at nodes, the energy is stored in the form of kinetic energy entirely, and the total energy must remain the same due to the conservation of energy. Now, if we consider an example where we have these standing waves being formed in a stretched string, then if I have a string which is fixed at this end, and there is one end which is free, so let's say that we have a string and I oscillate it something like this, then this is the free end of the string. Let me highlight it in green, and this dot is really the fixed end. The string is fixed, so you could imagine that you're holding the string with your hand over here, and then you're making it oscillate. So this fixed end is always where you will have a node being formed, while at the end which is free, you will always have an antinode being formed. Now, you could also consider another example where the string is really fixed at both ends, and if that's the case, then it would look something like this if I oscillate the string. So you could again imagine someone is holding the string at both ends, and when you do that, always nodes are formed at these fixed ends. And so if there are two nodes being formed, this would really imply that the total number of nodes is equal to antinodes plus 1. So nodes exceed the number of antinodes by 1, because at this point we are also getting a node instead of an antinode. Now we can talk about the speed of the wave speed of the wave in this string is really given as you can represent it with some v, and it is given as a square root of the tension which is being formed in the string when you're holding it from the either one end or both ends, divided by the mass density. It is also known as the linear mass density. So that's how you can find the speed of the wave that is being produced in this string when you oscillate it. Now, if we talk in terms of frequencies, then there is only a set number of frequencies that are allowed to be produced in these stretched string, really. And these frequencies are quantized as Fn is equal to n times F1, where this n can take values from 1, 2, 3, 4, and so on, right? While F1 is really the lowest, or you can say it is the fundamental frequency at which first stationary or standing wave is produced. And it is given by F1 is equal to 1 over 2L, where L is the length of the string times the tension in the string divided by linear mass density. And you can see that all the other frequencies which are they could be F 1, 2, 3, 4, 5, 6, really actually F2 star. So if F2, F3, F4, and so on, all of these are really just an integral multiple of the fundamental frequencies that are formed. And these F2, F3, F4, these are really given a name which is called harmonics of the oscillation, right? So these are the different harmonics of your oscillation which depend on the value of n. Next, we can discuss the case of these standing waves formed in pipes. We can have two different cases where we have closed pipes and we have pipes which are open at both ends, or it is just open at one particular end. So we'll see how these waves really form. So for example, consider you have a loudspeaker placed over here. It will really send sound into this long tube that you can see over here. And for example, if I place some dust in this tube, then the dust can show where we have nodes and where we have antinodes in this tube. Now nodes are really a half wavelength apart, as we saw, and so really even the antinodes are also half wavelength apart. However, the distance between from a node to an antinode is half of that half wavelength, which is just lambda by 4. And so if we look at this figure and we see where we have the maximum amplitude is just showing you the maximum pressure being varied and minimum motion of air in that part where we have the maximum amplitude. However, where we have the minimum amplitude, this point, in that case we have minimum pressure being varied and motion of air in that part is really maximum. Now you can see if you have a frequency which is very less comparatively to other frequencies, then the wavelength you can see clearly is larger. So you have a larger wavelength of sound being produced in this pipe. Now note that this pipe is really closed at both ends. It's closed at this end in this way that you have a speaker placed at this end very close to the pipe. And you can see the same case over here. The frequency is more lower, and so the wavelength is even larger. Right. So with that, you can also look at this one where we have pipe which is open at both ends. And in this case, sound can be reflected from an open end as well as from the closed end, really. And if you see this open end pipe, you see that we have the nodes being formed at these ends. And this is the way how those you might have heard of flutes or organ pipes. They work on this principle, really. And then we also have pipes which are closed at one end only, and these type of pipes, you can see that they are shorter. So now let's discuss the same thing again in terms of the frequencies, the length, the frequencies, and different harmonics for these. So for the pipes which are open or closed at both ends, right? In that case where we have this one, this is the case where here we have open and here we have closed at both. Either they're open at both ends or they're closed at both ends. So for this case, the length of this pattern being produced inside the pipes is just n lambda by 2. Really the length of the pipe is given by this expression, from which you can write down lambda as 2L by n. So that's the wavelength that would be produced in these type of pipes. And hence the frequency in these type of pipes would be given by V over 2L, where the V is the speed of the waves inside these pipes. And the different harmonics in this case, the only harmonics really which are allowed are of the form 2F, 3F, 4F, up to NF, right? So only these harmonics are allowed. So they are starting from 2F. Now, if I consider this case where I have pipes which are open at only one end, so these are those pipes, right? These are open at only this end and they're closed at this end. So in this particular case, we have the length of the pipe is given by 2n minus 1 times lambda by 4, from which I can find lambda, which would be given as lambda is equal to 4L by 2n minus 1. So that's the wave length that would be formed in this pipe, which is closed at only one end, or it's open at one end. Both mean really the same thing. And the frequency is given as V over 4L, where again V is the speed of sound waves being produced in this pipe. Then we have harmonics, and the harmonics that are allowed in this type of pipes are 3F, 5F, so only the odd numbers really, right? So 7F and up to, you can say 2N minus 1F. These harmonics are only allowed in these type of pipes, which are closed or either open at one end. Moving on, let's discuss the final topic of this chapter, which is known as the Doppler's effect. And the Doppler's effect really is, if you might have, you probably have encountered this before, if you are standing at a point, right? Suppose you're standing and you see that there is a car that is approaching towards you. When the car approaches towards you, suppose it's a police car and it has a siren on it. So there is a siren on this car, and the siren is on, and when the car is approaching you, it is, if it's getting closer and closer to you, then the sound waves that are being emitted by the siren, they are going to get closer towards you. And so for example, suppose this thing is getting closer and closer towards you. As it gets even more closer towards you, these waves start contracting, right? So they'll start getting congested simply because you are standing over here, and so the waves, there is this barrier between you, between, for the waves in front of them, which is really you, and so the wave starts getting congested. And so what that really means is, at this point the wavelength will start decreasing, which means the frequency of the sound waves really increase. And that's why when the car really approaches right by you, you hear the siren at very high frequencies. You must have really noticed that. Now, when the car just goes past you, and now the car has, you can say that now the car has really moved past you, and so you can say that now you're here and the car has moved past. So these waves that it has been emitting, now it's not being congested by anything. So because the waves are in every direction, so now the waves would be kind of like this, and they have passed you, so they're not congested anymore, and hence the wavelength now will increase, and so the frequency would decrease. And this kind of an effect is known as the Doppler's effect, which is really the apparent difference between the frequency at which sound waves will leave this source, which is the siren, at which they reach the observer. And it is really caused by this relative motion between this observer and the source. So I can write different expressions. So first, for example, suppose that the apparent frequency of the sound which is heard by the stationary observer or the listener due to this source which is moving towards him. So if I have a source moving towards observer, in that case the apparent frequency f prime is given as v divided by v minus us times f, where us is the source velocity with which the source is moving towards the observer. Us is that particular velocity, while v is the speed of the sound. So if the source moves towards the observer, then the apparent frequency is given by this expression. Now suppose that the apparent frequency of a sound which would be heard by the stationary observer, if the source was moving away, source moves away from the observer, what would happen in that case? In that case, the frequency would be very, very low, right? Because if it's moving away, that means the wavelength of these sound waves would start increasing, and so the frequency would fall, and so the frequency would be really less than, apparent frequency would be less than the frequency of the sound waves. And so the expression would be given by v divided by v plus us, where again us is the speed of the source which is moving away from the observer in this case, times the frequency of the sound emitted by this source. Furthermore, you could also consider a case where a person or this observer is moving. Observer moves towards a stationary source. So now this siren car is really not moving, and the person starts moving towards this car instead. So in that case, the apparent frequency would be given as v plus u naught divided by v times f, where u naught is the speed of this person with which he moves towards this stationary source. And then again, you could also have a case where this person moves away from the stationary source, and in that case the apparent frequency would be given as v minus u naught divided by v times f, where f is the frequency of the sound waves, and again v is the speed of sound, and u naught is the velocity of this person with which he moves away from the source. And then finally, you could have a case where both of them are really moving. And now suppose that if the source and observer move in same direction. So both of them are moving, but first case is where they're moving both of them in the same direction. Then the apparent frequency is given as v minus u naught, which is where u naught is the velocity of the person, divided by v plus us, where us is the velocity of the source, times the frequency of the sound emitted by the source. Next is source and observer move in opposite directions. So now imagine the person is moving in this direction while the source moves in this direction. In that case, the apparent frequency is given as v plus u naught divided by v minus us times the frequency of the sound wave that was emitted by the source. Now, we talked really in terms of sound waves at this point, but the point to be noted is that same thing is true for electromagnetic waves.